if you put a wing in air and run air over it, of course you get this difference in pressure and difference in velocity. And I thought the easiest way to show it to you would be to show you a couple of examples of what happens if you increase the angle of the wing, and then what happens if you bring a wing closer into ground effect. So if you start to increase the angle of the wing, on the left-hand plot, I have coefficient of pressure. That will tell you how hard the air is being pushed onto the surface. On the right-hand side, I have velocity magnitude. So this is a test done at 50 meters a second. So if it's green, yellow, or red in the right-hand plot, it's more than 50 meters a second. If it's blue or purple, it is less. And as we increase the angle of attack, you'll see the pressure and the velocity change. On the left-hand plot, I've also got flow lines. They drop out once in a while, and that's just a computational thing. But the flow lines are also really useful to tell you when you start to get the flow line. So at the back of the wing now, you see on the coefficient of pressure plot with the streamlines, you see that the streamlines are starting to separate. And on the right-hand plot showing the coefficient of pressure, the velocity magnitude, you see that there's an area behind the wing that is very, very slow moving, practically stopped. Practically stopped means if you are a car and you are punching through the air, you are taking the air with you. Yeah, but if you have a stationary wing and you're blowing air at it, then the air is basically getting close to stopped. And in these areas, you cannot follow anymore the Bernoulli effect because things are starting to let go. And as you increase the angle of attack, you get a bigger and bigger area that is starting to separate. Now, the truth is, going to this angle of attack, you still get increases in downforce, but you're starting to get it's starting to become inefficient. Then, if we have a look now, I've now got this up at 6 degrees, and then we have a look at what happens when we bring the ground up. So as you bring the ground up, a very similar thing happens. Now, what's really interesting about this is the drag on a body in the end has two components. One component is skin friction, and in motorsport, that's a very small part of the total. And the other component is pressure-induced drag. As you increase the angle of a wing, you are getting more and more of that suction force also pulling rearwards that creates then a drag force. Whereas if you put a wing closer into ground effect, the force pattern does change and the drag of the wing does actually increase a little bit. But the drag increases more slowly than if you increase the angle of the wing. You also get, even though this is a low angle of wing, you also start to get the separation bubble towards the end. It isn't as bad as it was, say, at the maximum angle, which was 16 degrees. Here at 6, it's not quite so bad, but you understand, you can get a feel for the concept that as you increase the angle of a wing, then or bring it into ground effect, you are creating a bigger adverse pressure gradient, we call it, and you are potentially needing to look for areas that are stalled.